chapter, we'll talk about the differences between linear and nonlinear equations. So these differences will be qualitative, and in a way we want to understand why linear equations are distinguished and why they're coined the term linear. So let's recall that the first order ODE is called linear if it can be written in the following specific form: dy dt plus dt times y equals qt. Well, here t is the independent variable, y is the dependent variable, and p and q are rather arbitrary. Okay, this is the form, and a general first order ODE that we consider of the form dy dt equals f of ty. Of course, linear equations are a very specific case. So this f of ty is very general, and only if it has the form, well, qt minus pt times y, then the equation is called linear. Okay, so what properties do linear equations have that nonlinear equations don't have? Now, the first and foremost property is the principle of superposition. Okay. So in order to discuss this concept, let's make a definition coming from linear algebra. So suppose that you have a certain number of functions of t okay, and also assume that c1, c2 up to cn are certain real numbers. Okay? Then a function of the form f equals c1 times f1 plus c2 times f2 plus so forth cn times fn is called a linear combination of the functions f1 through fn. Okay, so the recipe is multiply your given functions with certain constants and add them up. Such a function formed is called a linear combination. Of course, if you change the constants c1 through cn, the result, the combination changes. If an additional property is satisfied, if furthermore the sum of the constants equal to 1 is a special case, then it has a special name. It is called an affine linear combination of the given functions. Okay, this is a special case. The sum of the constants is equal to 1, but it's gonna pop up quite often, so it deserves a special name. Okay, now here is the principle of superposition for linear equations. You can think about this as a theorem. Okay, so our assumption is, let's say we have already some solutions of our equation. So say f1 up to fn are solutions of this linear equation y prime plus pt times y equals q of t. Then theorem claims any affine linear combination of these functions is also a solution. Okay. If f1 through fn are solutions, then any affine linear combination of f1 through fn is still a solution. By the way, there are many affine linear combinations because you can change your choice of constants c1 up to cn. Furthermore, if the right-hand side of the equation is 0, qt is 0, that's a special case, then you can drop the word affine. Then any linear combination of f1 up to fn is solution. So the difference between the two is, in one of them you have an arbitrary qt, it can be anything. Then the conclusion is slightly weaker. Any affine linear combination is a solution. If q is 0, then that's a stronger assumption, and the result is stronger. Any linear combination, you don't have to have affine, any linear combination is a solution. Okay. So the proof of this theorem is not hard at all. Let's do it. Well, f1 up to fn are solutions. This was an assumption, and the meaning of this assumption is that these equations should be correct. f1 prime plus pt times f1 must be equal to qt. f2 prime plus pt times f2 is also equal to qt. This goes on until the nth equation. Right? Okay, now we'll just multiply the first equation by c1, second by c2, so forth, the nth by cn, and add them up. Well, then group the terms together. Fortunately, derivative goes through sums, and also constants can be put inside derivatives. So if we add this up, we end up with the following thing. Here is this certain linear combination of the functions, derivative plus, you can also take pt terms out of all of these terms, and you'll have the same function here is equal to, this may not be visible. Well, on the right hand side, you'll multiply qt by c1, c2, cn, so forth, so you'll have this term here. Okay, now let us look at this closely. If this is your f, and the same f is here, so f satisfies the same equation if this number here is equal to 1, right? So let me put something here. So if the sum of these constants is equal to 1, then f satisfies the equation. And this is exactly the statement that affine linear combinations, remember that this condition was for being an affine linear combination, is a solution of the ODE. So we prove the first half of the theorem. If Qt is equal to 0, then you don't care about the value of C1 plus up to Cn because the right-hand side will be 0. So F is a solution regardless of the value of C1 up to Cn. And this exactly proves the second half. If Q is 0, then any linear combination is a solution. Okay, good. So this wraps up this important result. Now, this was the linear case. In the nonlinear case, we shouldn't expect linear combinations to be solutions in general. I mean, almost never will a linear combination be, again, a solution. Okay, now, m equals y squared. So this is certainly nonlinear. So we do not expect the principle of superposition to hold, but let's see this alive, okay? So this equation is separable. Or I can do the following. Okay. Now, the antiderivative of 1 over y squared equal to minus 1 over y. And on the right side, we have t, but we should also put plus a constant. Okay. Now, from here, we can solve for y. Y is equal to minus 1 over b plus c. Now, also, maybe we should mention, in the beginning, we divided by y squared. Therefore, we lost the solution y equals 0 there. And you can independently check that this is a solution. So y is equal to 0 is also a solution. And if you think about all possible values of c, you have a family of solutions here. And also if you include y equals 0, you have all the solutions. Now, let's pick two random members of this family, like y1 equals minus 1 over t, for example, and y2 equals, I don't know, minus 1 over e plus 2 maybe, okay? It doesn't matter which one I choose actually, or what I'll discuss. So linear combinations of y1 and y2, they look like this. Y equals c1 times minus 1 over t plus c2 times minus 1 over t plus 2. Now, is this again a solution of the equation? Well, if it were, y were solution of the equation, then it must be either of the form minus 1 over t plus c for some new value of c maybe, or y equals 0. Well, the second cannot happen. The sum cannot be identically 0 unless c1 and c2 are both 0. That's a special case. But let's look at the other one. If we have c1 times minus 1 over t plus c2 times minus 1 over t plus 2 equals minus 1 over t plus c for some c. So the question is, can this equation hold for all t? For some value of c? Well, this is hardly possible. I mean, if c1, c2 are non-zero, this will never happen, and both non-zero. This can't happen for a simple reason, actually. The left-hand side is a function whose domain misses t equals 0 and t equals minus 2, right? So look at domains, I'll say. The left-hand function will have two missing points in its domain, and you will have vertical asymptotes there. However, the right-hand side will have only one vertical asymptote at minus c, so these two functions cannot possibly match. So, in a sense, principle of superposition cannot hold. I mean, even if you make the restriction to affine linear combination c1 plus c2 equals 1, there are still many values of c1, c2, which are non-zero and whose sum is 1, for example, 1 over 2, 1 over 2, and in that case, you cannot get equality. So, principle of superposition completely fails. Well, you might say for special values like c1 equals 0, c2 equals 1, and you can take c equals 2 as well. But that's not what the principle of superposition says. Principle of superposition is more about all linear combinations with the constant satisfying either sum of constants equal to 1 or no condition satisfy the equation. So you should be able to move the constant. Here you cannot move the constant. Okay. So this is one crucial difference between linear and nonlinear equations. And another difference occurs in relation to an important result, which is the existence of uniqueness. This is interesting in its own right, but this is a good place to discuss. Sorry. So the question is, have y prime equals f of ty, some first order. This has usually many solutions because, I mean, with our experience, we know that whenever we try to solve this, some free constant will pop up somewhere and we'll have. But if you also put an initial condition, like y of t0 equals y0, now the initial value problem. Again, our experience so far in the problems that we solved says, okay, you find a free constant here, but when you plug in the initial condition, that tells you the value of the free constant. So you get one solution. Is this always the case? So let me write an abbreviation to this, IVP. Question is, do IVPs always have unique solutions? This is the general question. So this question has two parts. If I write an IVP like this, does it always have a solution? That's the existence part. And can it have more than one solution, or is it supposed to have just one solution, unique solution? That's the uniqueness. Now, we'll try to answer this question for linear and nonlinear equations separately because there are some differences. I mean, one could say that linearity is a special case. So whatever you want to say about nonlinear equations is probably still true here. But for linear equations, you can say much more. You can make stronger deductions. So let's look at the linear case first. So this is the existence uniqueness theorem. In the linear case. You have y prime plus pt times y equals q of t, and an initial condition yt0 equals y0. Now, I cannot say anything right away. I have to make some further assumptions, but they are not really extremely strong assumptions. So, suppose the two functions seen here, pt and qt, are both continuous on the open interval AB, and also assume that this initial point t0 belongs to AB. Okay, these are our assumptions. Your coefficient functions p and q here are continuous on a certain open interval, and your initial value belongs to this open interval. There are some natural conditions. And the result is that this is enough, okay? Then this initial value problem has a unique solution y of t, which extends, I mean, the first question is, does it have a unique solution near this point t0? That is correct, it has a unique solution, and that solution extends all the way to this interval. To I must say at least AB. If you are very lucky, it could extend even more, but usually not. Okay, now we can prove this theorem with the things that we know. We just have to remember how we solve a linear equation. This is something we discussed before. Now, if you remember the method of solution of linear equations, we defined an integrating factor mu equals e to the power integral pt dt. Then you multiply both sides by mu. And the point was the left-hand side becomes the derivative of mu t times y. Now we can integrate both sides with respect to t. And as a final step, we can divide by mu. Now, a few things to talk about. First of all, this existence uniqueness theorem is closely related to this free constant occurring in the solution. Where is the free constant? Now, that will appear exactly in this integration step, right? So when you integrate, you will have this integral is equal to some function, let me say f0 of t, some antiderivative of mu times q, whatever it is, plus constants over mu t. Here, f0 is an antiderivative of mu t times qt. I don't know what it is. It's going to be of this. Now, let's use our assumptions and analyze these steps a little bit closely. So now p and q are continuous, right? So we know from calculus that continuous functions are integrable. So p is integrable. So this e to the integral pt dt makes sense. And furthermore, the integral is continuous and the exponential is continuous. This is continuous. Right. Now, let's look at the other integral appearing. So integral mu times q. Integral mu times q dt. Mu is continuous. Q is continuous, so this product is continuous. So it is integrable. Right. I mean, there are some functions which are not integrable, but fortunately, continuous functions don't fall into that bad class, right? That's what we're checking. So this integration is theoretically okay, and the result will also be equal. There's no problem about that. Okay, whether or not you can find the integral, that's another question, but at a theoretical level, this function exists. This is an integrable function. Right. Now, okay, so you might be also worried about division by mu, right? But mu is an exponential. Mu is e to the power something, so it is never 0. So this tells you that this right-hand side, f0 plus C over mu. Okay, this is fine. There's no, actually it's continuous, let me say something. Continuous for any C. Right. Now let's come to the initial value business. If you plug in the initial value, y of t0 equals y0, does this tell you the value of the constant in a unique way? That's the question. So this is f0 of t0 plus c, or of course mu is also a function of t, so I have to put here t0 as well. Now solve for c. You'll see that there's only one answer here in terms of the other numbers. y0 times mu t0 minus f0 t0. So in terms of the given things, C is uniquely determined. So there's a unique solution. This is the end of the proof. Okay, so first, by these continuity integrability arguments, we saw that we can get this function, and then by plugging in the value, we saw that C can be found uniquely. This solves it all. Furthermore, everything that we discussed, so all this function was continuous on AB by the given formula. We just wrote down what it is. Okay. Now, let's pass to the nonlinear case. Here, y prime is equal to ft y. Well, this is quite general. In general, we don't know how to solve nonlinear equations explicitly, so we are in some slight trouble. How are we going to formulate the theorem? How to formulate the theorem? Now, linear case was when fty is of this very, very special form, qt minus et times y. Now, we want to sort of build an analogy with the linear case. So in the linear case, we assumed Q and P to be continuous, right? So, but in general, it is much more complicated, so we don't have such a Q and P. But the observation here is, if you remember Taylor series well, if we could expand F as a Taylor series in Y, idea, and F is a Taylor series with respect to Y. It's a two-variable function, but I fix one of the functions, variables, and expand with respect to the other. If we could expand, then in the linear case, Q and P would be, or minus P, analogous to the first two coefficients in the Taylor series, the constant coefficient and the Y coefficient. Okay, so PT is like, in a sense, or minus PT is kind of analogous to the partial derivative of f with respect to y, right, at y equals 0. But let me forget about that. So there's some analogy between minus pt and del f del y. If f is of this very special form, then del f del y gives you exactly minus p of t. So maybe we could get the same information as we did for p here by looking at del f del y. And indeed, that's what comes up in the theorem. This is existence uniqueness. General case or nonlinear case. Direct general. It's also true for the linear case, but in the linear case, we have a stronger thing anyway. So say we have y prime equals f of ty and y of t0 equals y0. Now, assume that fty and del f del y, as I mentioned above, this is still a function of two variables, ty, are continuous on, okay, where? Now, we have a slight problem here. In the linear case, we said that p and q are continuous on some open interval ab. But it's a little bit different here. These are two variable functions, f of ty and del f del y of ty. So speaking about continuity on an interval is meaningless. So I should rather speak about a two-dimensional domain. And the simplest that comes to mind is an open rectangle AB cross CD that contains the initial point E0, Y0. Now, the notation is very confusing because this is an interval. It's an interval. There's a Cartesian product, but there's a point. So sorry about this weird notation. I use the same type of parentheses both for interval and a point. These are the coordinates of the point t0, y0, whereas AB and CD are open intervals. Under this assumption, then there is a unique solution of this initial value problem. Good, but on unfortunately not on the given intervals or not anything related to the given intervals in general, on some open interval t0 minus h, comma t0 plus h for some h greater than 0. This is again an interval, not a point. Now, I want to draw a picture. Here's how we should think about it. AB, CD, the rectangle is the Cartesian product of AB and CD. It's somewhere here. And the assumption is your point with coordinates t0, y0 lives somewhere here. Okay. You assume that f and del f del y are continuous on a rectangle. Okay, on all of this rectangle, not just the point. And the conclusion that you make is you have a unique solution through this point, but does the solution go all the way to the boundaries of this box? In general, no. I mean, it might be sort of having some infinite asymptote here. Okay. This is maybe t0 minus h. Here somewhere you have t0 plus h. This t0 minus h, t0 plus h is not necessarily the largest interval, and the interval that the solution is defined doesn't have to be symmetric around t0, but it only says that you have some room for a solution. I don't know how big, but there's some room, and in that place you have a unique solution. Okay? It's a little bit different from the linear case, right? In the linear case, you could go all the way from the beginning to the end of the interval. In the nonlinear case, in general, you cannot. I'll give an example to that. Okay, now I want to give two examples. These are not problems, but these are rather examples explaining some of the details in this existence uniqueness theorem. So this first example is about if we do not assume continuity of the partial derivative, then the theorem may fail. I'm not saying that it has to, but it may fail. Here is the example. Look at y prime equals y to the power 1 over 3. Okay. You might say y 1 over 3. Well, I could have looked at 1 over 2, the square root of y, but you know, there's some problem about taking square roots of negative numbers. I don't want to think about that. The next simplest I can think about is 1 over 3. That's why. Okay, this is a separable equation, nonlinear, separable. And by the way, your f of ty is y to the power 1 over 3 here. We should actually think about it as a two-variable function, even though one of the variables don't explicitly show up. Okay, let's also look at partial derivative. Okay, you'll have 1 over 3 times y to the power minus 2 over 3. That's the partial derivative. Now, f is continuous on all of R2, the ty plane. Whereas the second function is not, because you have a negative power here, so this is like 1 over y to the power 2 or 3. So this is continuous on R2 except the line y equals 0. So if you want to draw your rectangles, well, you should sort of not include y equals 0 here. So this is t, this is y. your rectangle could be either up here somewhere or down here somewhere, right? On the shaded regions, both functions are continuous, but on y equals 0, the second function is not. Now let me show you that the uniqueness part of the theorem can fail if we select our initial point right on this axis. Okay? So suppose, switch to black, say y of 0 equals 0, okay? This point is on the bad place, right? So this is on the line where del f del y is not continuous. Now, let's try to explicitly solve this problem and show that there's more than one solution. So let me start over. Y prime is equal to y to the 1 over 3. Then this is separable dy over y to the 1 over 3 equals dt. Now, this is y to the power minus 1 over 3. And if you integrate it, you'll get y to the power 2 over 3 divided by 2 over 3. And on the right-hand side, you'll get t plus c. Now, we could solve this with some arithmetic. So I could say y to the power 2 over 3 is equal to 2t over 3 plus, let me say c again. Of course, here I renamed c because 2 over 3c and c don't make a difference here. And if you solve for y, you can get plus or minus 2t over 3 plus c to the power 3 over 2. Since 2 is an even number, you'll have either plus or minus square root. And y0 equals 0 gives you c equals 0. So apparently, we have two different solutions, plus or minus 2t over 3 to the power 3 over 2. Now the graph looks like this. I don't know if you ever graphed t to the power 3 over 2, but it is somewhere between y equals t and y equals t squared, so somewhere between a line and a parabola. In case it looks something like that. And it's negative will be its reflection through with respect to the t-axis. So both functions start from the same place, both satisfy the differential equation. So we have non-uniqueness, right? Solution is not unique. You might worry a little bit about the following. This is a little bit untypical, right? The solutions start somewhere and go to the right. In general, we had solutions defined on some interval containing this point. To solve this problem, you could extend these functions to the left with 0. So more precisely, set y1 to be 2t over 3 to the 3 over 2 if t is greater than or equal to 0, and 0 if t is less than 0, and y2 in a similar way, but with a negative sign this time. These are two totally different functions. They both satisfy IVP. So uniqueness fails. There's nothing wrong about the theorem because we cannot use the theorem. Its hypothesis is not satisfied, right? So the culprit, that's del f del y, is not continuous, right? So you cannot use the theorem because this was one of the conditions. If it fails, then the theorem doesn't say anything. And this explicit example shows that if you remove this continuity of del f del y, well, you have some statement which is not correct. Now, this was the first important example. And the second example that I want to give is about finite time blowup in the nonlinear case, or another way to say it is, we cannot replace this h greater than 0 in the theorem that you would remember by the whole interval of definition or whole interval of continuity. I mean, in the nonlinear case, you had this strange h appearing. In the linear case, you didn't. So you might say, okay, do you really need this h part in the theorem? Maybe it's superfluous. But this example will show that you cannot remove it, okay? It has to be there. Okay, again, I'll look at y prime equals y squared, which we looked at in the beginning of this lecture. Now we solved this and we got, so solved this before, and we got the following solutions. Either y is equal to minus 1 over y plus c, sorry, wrong, t plus c, or as a separate solution, we have y equals 0. Now, say y0 is equal to y0, and suppose that this is not 0. If y0 is 0, then we know that this y equals 0 must be the solution. You have uniqueness anyway, right? So this, in this case, f is equal to y squared, f and its partial derivative with respect to y are continuous everywhere. So through any point, we have a unique solution. And this is a good case for the existence uniqueness theorem. Nothing wrong at no point, right? Now, but let's look at how far the solutions extend. So if you plug these initial conditions in, you get y0 equals minus 1 over 0 plus c. So this will tell you that c is equal to minus 1 over y0. And to put it all together, we have yt equals minus 1 divided by t minus 1 over y0. Okay. Now, let's try to draw this on a plane. I can assume y0 is positive without much harm. I want to just show you an example anyway. So our initial point is here. When t is equal to 0, y is equal to y0. This is your point, 0, y0. Okay. At t equals 1 over y0, somewhere here, we have a vertical asymptote. So If you carefully look at the values of this function before 1 over y0, some number slightly smaller than 1 over y0 minus 1 over y0 will be small and negative. So if you do minus 1 over that number, it will be very large. So you can quickly deduce that the graph is going to look like this. Okay, so this has a vertical asymptote here. There is a unique solution through this point 0, y0. Here it is. Here is the graph. But if you wait a little bit more, it goes to infinity, right? So it explodes. So this domain of the solution or interval of solution is minus infinity up to 1 over y0, right? I can hear some of you asking, why don't you include, the right side of 1 over y0, because the function algebraically has nothing wrong there on the right of 1 over y0. That's okay, but we don't care. We are interested in where we can move from 0, y0 in terms of differential equations, and the right side of this asymptote has no connection to the left side, so we are interested in the connected component that 0, y0 belongs to. Okay, so we don't care about the right side. Now, if you look at f is y squared and del f del y are continuous on all of R2. So actually, in the hypothesis of the theorem, we could take this, remember this AB cross CD part. This can be taken as minus infinity plus infinity cross minus infinity plus infinity. Nothing wrong about that. So, I mean, these functions are nice everywhere, but the solution isn't, right? You have to select an h, but we should take this number h in the theorem to be something less than or equal to 1 over y0, right? This is still positive. I mean, 1 over y0 is positive in this case, fine. But we can, if we try to take it anything larger, the result would fail. So you need that h in the theorem. You cannot remove it. This is a strange thing. You start from a point, you have a very nice differential equation, but the solution suddenly explodes. This is a problem, both theoretically, I mean, you don't know how far your solution will extend, and also practically. You might have some nonlinear model, that could be some physical model. Okay, it works for small time intervals, but the whole system could explode a couple of seconds later, right? So, I mean, this is a serious problem. This finite time blow up is a serious problem, both theoretically and practically. It never happens for linear equations, but it can happen for nonlinear equations. Okay, so this is all I wanted to say. Thank you very much.